In this video, we will be extending the concept of differentials from 2 dimensions into 3 dimensions. So from back in Calc 1, the definition of a differential is given a function f of x, its total differential was referred to as dy, and it was equal to f prime of x times dx. The significance of this is that dy represents a change in y on a tangent line. So given a curve and given a tangent line, if we create a little tiny change in x, we can refer to that as dx or delta x. The actual change in y on the function was referred to as delta y, whereas the change in y on the tangent line was referred to as dy. Now, as long as dx is small, we'll say, relatively small, then dy was approximately equal to delta y, in the same sense that the tangent line is approximately equal to the actual function. Now, in 3 dimensions, if z is equal to f of xy, the total differential of z is total differential. This would be dz is equal to, this will be the partial derivative of f with respect to x evaluated at whatever point is given to you, times dx, plus the partial derivative of f with respect to y evaluated at whatever xy is given to you, times dy. It's essentially the same formula as before, but now since we have 2 independent variables, we will need 2 different partial derivatives. Now what this does is dz represents a change in z value on a tangent plane, as opposed to the tangent line that we referred to from earlier. Now what I'd like to do is give a little bit of context to this by referencing back to one of our previous videos. In one of our previous videos, we had established all of this lovely information. This was find the equation of the tangent plane, blah de blah de blah. I just wanted to put some things into context here. Now, for example, down here when we say that the linearization is equal to this formula right here, what we actually had here was z equals a specific z0 value plus this 4 represented the partial derivative of f with respect to x. This x minus 2 could be interpreted as a change in x. And then this 6 represented a partial derivative of f with respect to y, and then y minus 3 would represent a dy. Now also within the context of the problem, you'll notice that we started at the point 2, 3, and we moved to the point 1.97 and 3.05, telling us that dx in this case would have been equal to where we stopped minus where we start, so 1.97 minus 2, so the overall change in x was equal to negative 0.03. For the y value, we started at 3, we ended at 3.05, so dy would have been 3.05 minus 3, for a total of 0.05. You'll notice that this negative 0.03 and this positive 0.05 also made an appearance at the end of the problem. That was this quantity right here, dx, and this quantity right here, dy. Now with that in mind, here is the actual z value for the function, and here is the z value at the initial point. So if we take this and interpret it as z, and subtract this 13 over to the other side, we would have z minus z naught, which can be interpreted as dz. So the formula for finding this total differential is actually incredibly similar to the process of finding the equation of a tangent plane. Now, a cool thing about differentials is differentials also allow us the opportunity to do error analysis. Or, as you'll probably hear in engineering classes, tolerance. I don't actually know if I spelled tolerance correctly. I don't know if that's supposed to be an A or an E. But regardless, when you are measuring quantities or constructing things in an engineering class, you're allowed to create something within a certain amount of tolerance. So that tolerance is essentially an error in the calculation that you're doing. This is where things like significant figures could come into play really easily. Now, we'll run through that with a couple of examples. We'll do one where we're just calculating a differential, and then one where we're bringing in error analysis.